12.3. These are the free response questions from the year 2000, 20 years ago. But calculus, sort of foundational. It's not like changing a lot. At least it's basic ideas. So, the AP test does change, and they change what they cover, and they change the way they ask questions, the things they expect, and I'll always point that out to you. If I'm doing old problems, I'm going to make sure and do them, to the level that you would be expected now. Now, graphing calculator is going to be required for the first problem and the second problem. Generally, calculators are, it's the first two problems, and you have 30 minutes, 15 minutes each, roughly. 30 minutes, you lose your calculator, but you can still work on the problems, but now the clock is ticking for the last 60 minutes of the last four questions. But you want to make sure you get your calculations done before the 30 minutes runs out, and then maybe fill in the answers better after that. Okay, let R be the shaded region, the first quadrant. Sometimes these graphs, like if we didn't state that, then these graphs keep going into the second quadrant, and that would be part of what we're looking at. The graphs are already labeled. A lot of times they aren't. If they weren't, I would put them on there. X-axis, as shown here. Find the area of the region. We could, find the area with vertical slices, y top minus y bottom, to make sure it comes out positive. Even though we're allowed to use a calculator, you have to show the setup. So the setup for the area is going to be, hold on. Before we do that, we need our limits. So this is 0, 0. This is 0, 1. We could plug 0 into that, and e to the 0 is 1. We don't know that intersection, so we got to find that intersection. It's up to you. I think we could go and just graph these, and putting these in the y menu might save us a little time later on. Anyways, e to the negative x squared, and then 1 minus cosine x. Make sure you're in radian mode. Go to window. Now, the nice thing is we have a window of what we're interested in. So we might say, all right, -1 to 1.5. Just to see the y-axis, I do -1, y min, -1 to 1.5. Graph it. And it should look like that. If you enter them wrong, it'll be obvious. I guess that's one benefit of graphing it. And now we can find the intersection point. Second, calculate. Number 5, intersect. You got to identify the curves you want to find the intersection of. You need two curves. They are always going to ask you, if there's only two curves, it's inner, inner. Otherwise, if there's three curves, you got to pick which two. And then a guess. Now, we could use the cursor all day long or be like, that looks like it's around 1, which is a little quicker. And so I'm going to put this on my picture, 0.9419448 and 0.41178,305. More decimal points than 3. Now, anything you draw in the picture is probably not going to get you any kind of credit. So it would probably be good to show what you were doing, because, that's an important thing where we set the equations equal to each other, and we get x equals 0.9419448 and 0.41178,305. Just to have those. So that's the x and the y value at that intersection. Okay, now back to what we're doing. We're trying to find the area. So the area is the integral of 0 to 0.941944. 6 decimal points is definitely enough. And we're going to do the top curve, e to the negative x squared, right? Make sure it's the top one, minus the bottom curve. Now you got to subtract the whole bottom curve, so you got to put parentheses around it, or at least distribute if you're going to skip putting the parentheses. This is good enough for the setup, and you have to show this to get full credit. And the finding the intersection was actually worth a point. So you kind of want to make sure you have the work for that, the setup for it, that you wrote it down, besides just having it on your picture. 1 point for the setup, and then it's going to be 1 point for the answer. Second, okay, quit. So I'm going to do this on the home screen. So I'm going to do math 9 vars y vars function y1 minus vars y vars function y2. Make sure you remember which one is in the first. I entered the first one. I generally try and enter them in order so it's easy to remember where they're at in my y menu. Comma x, comma 0, comma point 941,944. And our answer is 0.590 or 0.591 if you want to round, but I generally avoid that. So that's a point for the answer. Or you could do horizontal slices. I don't think it's probably a great idea here. X right, X right. Now, the thing that happens that's a little more challenging for horizontal slices is that you're going to have to break them up at this intersection point. So to find the area with horizontal slices, which just might be good practice right now, just to try it, the first chunk is going to be 0 to the y value of the intersection, 0.411783. It's going to be x right. Now, x right, that's this cosine curve. So to solve for x, you would say, all right, well, cosine x equals 1 minus y, and x equals inverse cosine of 1 minus y. So it would be inverse cosine of 1 minus y, and x left is just 0 on both of these. So we don't need to write that down. So that would be, and then dy, and then you would add the next one starting at the intersection point 411783 up to 1. And the right curve, you'd have to solve for x. So you'd have to take the natural log of both sides, and then you would take the negative, and then you would take the square root of both sides, plus or minus, and it's going to be the positive because these are positive x's. And this graph kind of has a symmetric look to it. So the right half is the same as the left half, but the left half would be the negative values for x. If you plug negative x's in here, you get the same as the positive x's. So we want the positive one for x right there. So that's going to be square root of negative natural log of y. And you might be like, well, we can't take square roots of negatives. Yeah, but natural log of y could be negative, and it is for sure between 0, when y is between 0 and 1, which it always is. Minus x left, which is 0, dy, and that could be your setup. Now, you guys wouldn't be able to integrate either of those by hand, but guess what? Your calculator can do it. So let's see if we can get the same answer. We should get the same answer. Math 9 inverse cosine of 1 minus x, putting x's, comma x, comma 0, comma 0.411783 plus math 9 square root of negative natural log of x, close, comma x, comma 0.411783, comma 1. Enter. So we should get the same area. Seems like this is a little harder for the calculator. And sure enough, 0.590 or 0.591. So two different ways. You only have to do it one. I would definitely go with the vertical slicing there. The horizontal slicing was a bit annoying, but possible. Not by hand, but with the calculator. Find the volume of the solid generated when R is revolved around the x-axis. Okay, so I'm going to redraw the picture here. Not that the picture isn't going to get you any credit, but it's going to probably help you get credit by getting everything right. So I find pictures very helpful here. So I'm just going to try and sketch these curves just roughly. Okay, something like that. Now the intersection is, I mean, we could write that there, 0.9419440.4111783. This is our area. And I mean, I think it's just worth it to spend, a little bit of time to get that. Now it's being revolved around the x-axis. Make sure you revolve around the x-axis. I like to draw a little thing here. Now, I think the best way to get the other one is to put the intersection points first and then kind of connect the dots. Okay. And so we can do disc washers or we can do shells. So if you're going to do disc washers, I'm going to just try and fit both on the same picture. You're only going to do it one way, so you only need one picture, but I'll do it both ways. So if you go perpendicular to the axis rotation, you're going to get washers, right? And so the volume of a washer, don't memorize it. You're looking at a circle with a thickness, so it's the area of the circle, pi r squared dx. And then there's a smaller one that you guys subtract pi little r squared dx. And then we're going to integrate them. Now, this is the big R and this is the little r. So the big R is y top minus y bottom. The little r is y top minus y bottom. It's a vertical length, different y tops and y bottoms potentially. That's why we have the picture. The volume is going to be, the limits are going to be in the x direction, 0 to 0.941944. The big radius is y top in terms of x. Now, might be helpful to go ahead and just label these graphs again. Y equals e to the negative x squared, and this one is y equals 1 minus cosine x. So the first y top is e to the negative x squared minus y bottom is 0 squared dx. You could put these in the same integral if you want to combine this all together, but you don't have to. The little radius y top is that 1 minus cosine x curve, and y bottom is 0 squared dx. That's your setup. And that is worth 2 points for the setup, and then you're going to get 1 point for the answer, which you're going to just do on your calculator. Now, could you integrate these by hand? No. You can't do that one. You could do this one. You're going to plug those ugly decimals in? No. Use your calculator. So we're going to do pi. I just put everything in there. Pi, math 9, parentheses, e to the negative x squared. I guess we could totally do vars, y vars here. Because I already have these inners squared, comma x, comma 0, comma 0.941944 minus pi math 9 parentheses 1 minus cosine x close squared, comma x, comma 0, comma 0.941944 close. 1.746 or 1.747 if you really want to round. The other way we could do it is with horizontal slicing. And again, this is going to be a pain because the horizontal slicing have to change at that intersection point, just like they did last time. So you're going to get two different sets of shells. I'll show you, but I don't think that this is going to be the fastest way. But with shells, the volume of a shell, it's like a tube, and you slice it open, and it's a rectangle, right? I mean, just use your paper and be like, okay, here's a tube. This is a shell. And if you slice it open, you get a rectangle. And the area of the rectangle times the thickness is the volume of that slice. The area of the rectangle is 2 pi r, because the top length of the rectangle is the original circumference of the shell, h, the height of the shell, the height of the rectangle, dy. And then we're going to integrate. Now, for us, we're going to have to go 0 to 0.411783 for the first ones. The radius is y top minus y bottom. It's whatever y we're at minus y bottom, which is 0. So it's just y. The height is the thing that depends on the shells. It's x right. This first one is x right minus x left. So it's x right. It's that cosine one that we wrote earlier. Inverse cosine of 1 minus y minus 0 dy. And then we have to add the next one, 0.411783 to 1. The radius is still y. The height is x right minus x left, x right minus x left. So it's this x coordinate of the e to the x curve. And we solved that earlier. That was positive square root of negative natural log of y minus x left at 0 dy. So that is your setup, which would give you the same points, amount of points. And so we could put that on our calculator. Now, we couldn't integrate that by hand for sure, but our calculator can do it because it's using slicing and it's using estimation techniques. 2 pi math 9 x times parentheses, or I don't know, we just say times inverse cosine of 1 minus x. Oh shoot, I don't know what happened here. 1 minus x, close those parentheses, comma x, comma 0, comma 0.411783, close, plus 2 pi math 9. We're putting x's for the y's, x square root of negative natural log of x, close, close, comma x, comma 0.411783, comma 1. That's a lot to type in. And we should get 1.746. There it is. 1.746. 1.747 if you round. Okay. So this is taking a little while longer because I'm doing each problem 2 different ways. The region R is the base of a solid. Now, my pictures are getting really messy, and my pictures aren't to get me any credit. Okay, you have to show all the setups, but the pictures are just helping you get everything looking right. So I'm just going to redraw it again real quick. This is the 1 minus cosine x curve. This is the e to the negative x squared curve. Your endpoints, your intersections are those. It's the same area we've been working with since part A, but it says that it's the base of a solid. For this solid, each cross-section is perpendicular to the x-axis and it's a square. So that means they have to be vertical slices, and they are squares. So there's one slice, and you want to find the volume of all those. So the volume is the the interval of the area of each of those slices that has the same kind of formula times the thickness. In this case, they are squares, which have a formula side squared. The limits are going to be left to right 0 to 0.941944. You always want the dimensions of your shape to come from the bottom of the slice that's in the region right here. And so that's going to be y top minus y bottom, y top minus y bottom. And y top is the top curve is e to the negative x squared. Y bottom is the 1 minus cosine x. You got to subtract the whole thing. I'd put in parentheses dx. It's got to be squared. Don't forget the squared. So there's your setup. And then we're supposed to calculate it. So we're going to do on our calculator, math 9. And we can do vars, y vars if you want. Y's var, y vars, y1 minus vars, y vars, y2 if you have them entered. Now we do need to put parentheses around them. So second insert parentheses, you need parentheses around them, and then you need to square them. Comma x, comma 0, comma 0.941944. And we get 0.461 rounded truncated 3 decimal place accuracy. Turns out the same. It's 2 points for the setup, 1 point for the answer. So if all you do is put answers and you don't put the setups, you're going to lose most of the points. So that's just a good review of what we were doing in the last couple chapters. Problem 2, we have another calculator problem. This one is it says two runners, A and B, runner A, runner B, run on a straight racetrack for 0 to 10 seconds. So this right now you should be thinking, oh, this is rectilinear motion. This is one-dimensional motion. So I'm going to have to use that information. The graph above, which consists of 2 line segments, so it's piecewise graph, shows the velocity. So this is the velocity in meters per second. So we're going to have to put units in our answers of runner A. So this is just runner A. So you might say V sub A. Velocity in meters per second of runner B is given by the function V. So they give you a formula they give you an equation for the velocity of B, but then give you a graph of the velocity of A. So we're going to probably have to switch modes and be able to use graphs and sometimes use find the velocity of runner A and the velocity of runner B at t equals 2 seconds. Indicate units of measure. You're going to lose points if you don't put it. Indicate units of measure. Indicate units of measure. If you leave off units, you're going to lose unnecessary points, and that's going to be sad. So the velocity of runner A at 2 seconds is going to be whatever, let's see, this is the velocity of runner A. I mean, this is the velocity at 2 is going to be whatever value this is right here. Now, it's kind of hard to tell from the graph, and you shouldn't be like, oh, that looks like it's 6.5 or whatever. There's a way that you can do it. You could find the slope of this line. It's up 10 over 3 and multiply by the number of times over. So you're going up 10 over 3, okay? And if you multiply by 2, then that's going to give you how much of that fraction. So it's a ratio of 10 to 3 for every 1 unit over. So that's going to be 20/3, or on your calculator 6.666 or 6.667. The units are meters per second. Velocity is distance, velocity is length over time. So that's that one. That's 1 point, which should make sense. Velocity of B, we're going to use the formula. So we're going to plug 2 into it. And you don't have to put the decimal answers, by the way. If you have the exact answer, that's fine too. 48 over 7. That's good enough. I mean, you could just leave it 48 over 7, but if you do use your calculator, it'd be 6.857 rounded or truncated meters per second. Make sure you put the units. If you don't put the units, you're losing points. And there's not worth a lot of points. So that's pretty straightforward. B, find the acceleration of runner A and the acceleration of runner B at time t equals 2 seconds. Okay, well, acceleration is equal to the derivative of velocity, right? And so if you want the acceleration of A at time 2, that's going to be the slope of the velocity at time 2. And so we're looking at this picture and we're saying, well, what's the slope there? Well, we just figured it out. It was 10/3, right? Or 3.333. And the units are going to be meters per second squared. Acceleration is the derivative of velocity. So we're taking the derivative, the change in velocity with respect to time again, so you get seconds squared. The acceleration of B at 2 is going to be the derivative of the velocity of B at 2. And this is all good stuff to write. This is telling me you understand the calculus. You don't want to like be lazy on these for your response. It's all about the work you show. It's not the answer itself is generally worth the least amount of points. Okay, so this one, I guess I should have started over here first. A sub B t equals V sub B derivative of velocity. And so we can take the derivative of that. Now that's going to be quotient rule, low d high minus high, low d high minus high d low all over low squared. Now I'm going to tell you in a second that we really shouldn't be doing this because your calculator can do derivatives. So we don't need to do this. I'm going to actually stop right now. Now, I'm going to put this equation into the y menu just in case I need to use it again. 24x divided by, definitely parentheses, 2x plus 3. And so we could, on this screen right here, say math 8 and derive vars y vars function y1, comma x, comma, you want the derivative at 2? There it is. That was way faster than what I was about to do. And also, I was probably going to make some mistakes if I kept doing that work. So please don't do that. You have a calculator. Of course you could do that. It's going to give you the same answer eventually. I mean, if you kept simplifying this, it'd be 72 over 2t plus 3 squared. And then you can plug 2 into this and you would get the same answer, right? You would get 72 over 49. Okay, well, what's 72 over 49? 72 over 49 is the same answer. But you need to start to realize that you want to take advantage of your calculator as much as possible. Find the total distance of runner A and the total distance of runner B over the time interval 0 to 10 seconds to indicate units of measure. So how do we find total distance for one-dimensional motion? We integrate the speed, which is the integral of the absolute value of velocity, right? And so if we want the distance for A, we're going to integrate from 0 to 10, it says, and it's going to be the absolute value of the velocity integral, which for A, we're having to use this graph. So how do you find the integral of this graph? Absolute value would force everything positive, which it is, and then you would find the area underneath it from 0 to 10. I personally would break that up into a triangle, 1/2 base times height, and a rectangle. You could do one big trapezoid, by the way. The rectangle, this is 7 times 3. Now, I would show this work down here, okay? I mean, it's great. Anything you want to write in your picture to help you use the right values is good, but so that's going to be 15 plus 21 is 36, and distance should be meters for the distance of A from 0. Now I made a mistake somewhere. Let's see. What did I do? No, I think I'm good. I think I made a mistake on my original solution. So I think that's the right answer. Someone in the comments point out if I made a mistake. I'm probably not going to redo the video, but 0 to 10 of the absolute velocity of B, which is going to be 0 to 10 of the absolute value of 24t over 2t plus 3 dt. I don't think you guys want to integrate that. I don't think you can. And even if you could, just use your calculator. Now, with integrating absolute values, by the way, by hand, we'd have to break it up. We'd have to figure out where it changed signs and forced it all to be positive. But your calculator can do this really well. So math 9, math num, ABS. We could do vars, y vars function y1 because I haven't entered. Close, comma x, comma 0, comma 10. But you have to show this setup. Okay, and then you don't have to tell me what buttons you push on your calculator. 83.336 meters. Put the units, put the units, put the units. Label your answers. Tell me which is which. So show your setup. So there you go. That's it. The points, there was 4 points here. So there was a point for showing this kind of work, and 1 point for your setup, and then 1 point for your answer, and 1 point for your answer. So nice problem involving motion, but also involving the graphs of derivatives, the graph of a function, having to integrate from pictures, having to integrate from equations using your calculator. Now, this next problem is, generally, you're always going to get a motion problem involved in one of your free response questions out of 6. You're usually going to get an area volume problem, which we already did. You're going to have 2 calculated problems, which we've done. You're going to have 4 non-calculated problems, which is what we're doing now. You're generally going to get one of the free response questions is going to be the graph of the derivative. The figure shows the graph of f prime. Now, it's been a little while since we've done this, but we can analyze functions from their graphs of their derivatives and describe things that are happening on the original function. So the derivative of the function from -7 to 7, the graph of f prime has horizontal tangent lines at x equals 3, 2, and 5. So they're telling you that. I mean, I feel like that's pretty obvious looking, but then that verifies exactly what values that those are happening at and that they are flat. And a vertical tangent line at 3. Interesting. Now, I would do what I'm doing here and write those things on there. Okay. So A, find all the values of x from -7 to 7 at which f attains a relative minimum. Justify your answer. Now, how are we going to justify relative minimum? Probably first derivative test for relative extrema. Potentially second derivative test if we can do first derivative test. So where do relative mins happen? Well, you have to. I mean, we could look at it right here. This don't tell me there's a relative min at -3 and 5. This is the graph of the derivative. We're trying to say for the original function. So what we could do is what we've done before is kind of analyze this graph. Now, anything we write on this graph isn't probably going to get us any points. We got to put it. We have to then describe it in our answer. So this is where the derivative is positive, increasing, negative, decreasing, positive, increasing, positive, increasing, right? This is a critical point at -5. This is a critical point at -1. This is a critical point at 5. The graph is going up and then down. This is a relative max. The graph is going down, then up. This is a relative min. The graph is going up, flattens, goes up. This is neither. This is like a plateau. All right. You guys remember doing all that stuff? Here we are. We're doing it. Now, right there is the relative min at -1. So I don't think that's that hard, but we got to put it in words. We could say at x equals -1, f has a relative minimum. And so I think maybe we should point out that it's a critical point since it has a critical point at x equals -1, f prime of -1 equals 0. And then we need to describe the first derivative test. It says at critical points, which we've identified, if the slope, the derivative changes from negative to positive, you get a relative min. So we got to put that, we got to describe that. And f prime of x in general, don't put -1 here, is negative. You could say is negative, or you could say it's less than 0 for the chunk to the left of it. So I'm going to be specific. I'm not going to just say to the left because it's not negative to the left of it everywhere. It's positive eventually. So I'm going to describe the interval and then describe that the derivative is positive on the right side for -1 to +5. So that's a good answer right there. That's how you have to justify your relative maxes and mins. You have to use first derivative test for relative extrema. I mean, I guess, you know what we should maybe even say is by the first derivative test for relative extrema. If you look in old scoring guidelines, they usually wouldn't bother to name it for these kind of problems. But if you look at more current guidelines from the last couple of years, they generally are naming them. So, I mean, just to be safe, I would just name it and describe how it works. B, so just minimums, by the way, don't do maximums. B says find the relative maxes and justify your answer. So same idea, we already did all the work, so we just need to put in an answer. We can say at x equals -5, f has a relative maximum. Don't just say maximum because that indicates absolute maximum. Relative maximum, since it has a critical point. So all the stuff that we wrote up there to help us decide that, we need to put that into words down here. Critical point at x equals -5. We could describe exactly what kind of critical point is, that it's 0. And f prime of x is positive for the interval of -7 to -5 on the left, and f prime of x is negative for the interval directly to the right, -5 to -1, by the first derivative test for relative extrema. Okay. 2 points, 2 points, 2 points, 1 point for the answer, 1 point for the justification. Part C is 2 points. Part C says for all the values, find all the values of x where the second derivative is negative. So we're looking for where the second derivative is negative, which also corresponds to when it is concave down. Now, not where this graph is concave down, where the original graph is concave down. Now, I don't know if you guys remember, we can identify concavity, the original function, from the graph of the derivative. The concavity comes in the second derivative. The second derivative is the derivative of the first derivative, which we have a graph of here. It's the slope of the slopes. So here, f double prime is negative, concave down. Here, f double prime is positive, concave up. Here, now actually, you might say, oh, f double prime is negative here because it's concave down the whole time, but you have to break it up at 3 because there's a vertical tangent, because the second derivative actually doesn't exist at 3. So you can't say anything. Concavity doesn't exist there. Here, f double prime is positive, concave up. Now, anything we write on here, that's not helping us get points. So we need to write our answers. We need to interpret it, and justify it. So we could say that f double prime of x is negative on, what are the intervals that's negative on? -7 to -3 do not include the endpoints. The next one would be 2 to 3. And the last one would be 3 to 5. So you have to break up 2 to 5, 2 to 3, 3 to 5, because it's not defined right there. And I would explain why. Since the graph of f prime, so explain how you're taking the information they gave you. This is the graph of f prime. What about the graph of f prime leads you to believe this? Since the graph of f prime is, and the best way to say it, instead of saying the slope of it, I think it's better to say it is decreasing, which means it has a negative slope, negative derivative. It's decreasing on those intervals. And that I think that's your best way. Don't say second derivative test. This has nothing to do with second derivative test. This is second derivative. It's concavity. Second derivative test is for identifying relative maxes and mins, which is not what we're trying to do here. Don't just, D, at what value of x does f attain an absolute max? Absolute max. Okay. So that's a trickier, it's tricky to justify, because usually with absolute maxes and mins, we do extreme value theorem, right? We say, okay, well, we want absolute max, and we could show some work to help us kind of wrap our head around it. You want endpoints, which you are given. You want critical points, absolute max of f of x. You want critical points, which is going to be when f prime is equal to 0 or undefined. And we already identified those earlier. That's x equals -5, -1, and 3. Not where this graph has 0 or undefined slopes, but the original graph, which is the x-intercepts of this graph. And then, we usually make like a table. We say, all right, here's the x values. We're going to plug these into the original function x, which we don't have. That's the hard part here. And the endpoints are -7, -5, -1, 3, and 7. Now, we don't have the original function, so we actually can't find these values. We don't have an initial condition. We can't find the original function. But what we could do is we could say, well, let's start at c. A lot of times we start at like a c value constant integration at -7. So from -7 to -5, we're going to add the integral of the integral of f prime of x from, say, -7 to -5 gives you f of -5 minus f of -7. And what that gives you is the change in the function from -7 to -5, and you would add that chunk right here, right? And that would be the area under the graph of the derivative. So this area right here tells you how much the graph goes up, but then it goes down a bigger chunk. So this is, and this was a relative max, by the way, right? And then it goes down even more. So we're now less than the original starting point, right? And that's a relative min at -1. And then we go up a bunch. So now I think we're back to greater than the original point, the highest point on the graph, because the amount we went down here, we went up more than that. So we should be higher than that last high point. And then we go up even more. And so I'm saying right here, this is the absolute max, right? So I can figure that out looking at the area. The graph goes down a little bit, goes up more. I'm sorry, the graph goes up a little bit, goes down more than went up, goes up even more than went down. So we're now back up to past that point, and then goes up even more. So we're at the highest point on the right side. Now, putting that into an answer is tricky because this table with our just vague ideas isn't good. But I mean, this is maybe a way that you could try to explain it. The absolute maximum must occur at a critical point, and maybe I'll go and list those. A critical point x equals -5, -1, 5, or an endpoint. So it might be good to, to state, the places that you have to consider. And then we could say, well, f of -5 is greater than f of -5 is greater than f of -7 since f is increasing because the graph is going up, right? The derivative is positive, so the graph went up. So we definitely got to be higher there. And then f of -1 is going to be less than f of -7 since f is decreasing, and the magnitude of the negative change from x equals -5 to x equals -1 is smaller than the positive change from x equals -1 to x equals -5. Anyway, I'm just putting all that into words. I mean, this is kind of hard. So, and then f of 5 is bigger than f of -5, or is big, is bigger than f of -1, since f is increasing from x equals -1 to x equals 5, and f of 7 is even greater than f of 5 since f is increasing from x equals 5 to x equals 7. So f of 7 is the absolute maximum. Okay, this is the maximum value, the absolute maximum value, and the location is at x equals 7. By extreme value theorem. Maybe we should mention that. We already kind of mentioned the guts of it. So, anyways, this was annoying. It was worth 3 points. So if you get to, don't stress out. Just, okay. Usually I feel like more nowadays, they would give you the area of these chunks. So then you could actually find the values there, and it wouldn't be so vague and like, well, this area is bigger than that area, which is, So anyways, I'm going to stop this video and do the next problems on a separate video. But you would have been given 45 minutes to do these first 3 problems, and we've done about that amount of time. And some of the problems we've done multiple ways. And I'm trying to go into detail. I want you to know exactly what you're being asked for. I want you to try these problems before the videos, and then as best you can, and then watch the videos and finish them up.